Welcome back. In Module 3, we will discuss how to apply the two principles that we have learned in the previous two modules to the development of software. The outline of this module is as follows. First, I will give you a brief description of what I think software development is. Then we will go through the software lifecycle. I will discuss the object-oriented analysis and design within the context of the software lifecycle. Then I will talk about object-oriented notation that is useful for the analysis and design stages. We will give a small example to illustrate some of the concepts that we developed in the previous 4 items, and finally we will summarize. Software development involves creating cost-effective solutions to practical problems by applying fundamental software principles. What does that mean? If you look at engineering, in engineering we do create cost-effective solutions to practical problems, but we apply fundamental engineering principles. I don't call, many people call this as software engineering, but I tend to use the word software development because engineering means something to me. However, in this module I will wear my software hat and I will talk about software development. In our lab, we have had considerable experience in building large scale software systems using certain principles of object-oriented development, and I will share those principles with you in this module and in later modules. There are certain inherent properties of the software that make software a very complex beast. The main properties are complexity, conformity, changeability, and invisibility. As Fred Brooks said, complexity is an important aspect of software development because software entities are more complex for their size than perhaps any other human construct because no two parts are alike. This is a quote from Fred Brooks in a paper called There is No Such Thing as a Silver Bullet. But let's have a look at the difference between this concept of software development and engineering products. Well, if you take a bridge, you will not have a sign in front of the bridge saying that beware, you are crossing the bridge at your own expense. On the other hand, if you buy a piece of software, you will always see a disclaimer in front of software. One can argue that in the contracts which are in the engineering with the engineers, there are all these things somehow or other placed in implicitly somewhere so that the blame is always assigned on someone else. However, let's leave that aside and come to the aspects of this particular module. The second aspect is conformity. In engineering, if you look at engineering artifacts, they conform to certain physical principles. However, software does not conform to any physical principles. There are no physical principles underlying software. It is also ironical that when we design large engineering systems, we use analysis packages which are really software packages to test whether these buildings are going to stand or not. The next aspect of software is changeability. Software is very malleable and it can change a lot over the time. For example, if you buy a Ford car or a GM car, it's very rarely that they change the models very frequently. However, for software these changes occur rather frequently. Finally, software is invisible. In engineering products we have certain geometric abstractions, and you will see in module 5 of several examples of some geometric modelers. However, software is invisible. There is no geometric abstraction to software. So all these inherent properties of software make software a very, very hard thing to implement. Let's look at the software life cycle now. So if you look at this software life cycle, it's very similar to the life cycle that we have mentioned for engineering product development, where we start with market needs, that is we do a market analysis, and this is followed by the conceptualization stage, which is followed by the functional requirement analysis stage. In the market analysis stage, we go out and find whether there is a need for this particular product. For example, spreadsheets. We can go in and find out whether people really need spreadsheets or not. In the conceptual design stage, we zero in on a particular product. Then in the requirement specification stage, we set the functional requirements for this product. In the design stage, we provide the detailed design of the product. In the coding stage, we code. And in the integration and testing stage, we try to make sure that all the modules that have been developed in the coding stage are integrated properly and then tested, so to make sure that there are no bugs. Then we go to the marketing stage and sell this product, and finally there is a maintenance stage where we maintain. Although we show this stage as a lonely stage, the maintenance many times may cost more than the product development, and you have to keep in mind, and that's the reason why our object oriented software development is useful, because it's easy to maintain. So if you look at this cycle, this is a kind of an iterative process, just like our engineering process, and it's also a collaborative process. People tend to use the name waterfall model to depict a model such as this, but I'm just using the name traditional cycle because this not only shows you the iterative steps involved in the software product development, but also the collaborative steps. In traditional software development, to make sure that we develop good pieces of software, there are a number of principles that we need to adhere to, and here are certain key software development principles, and I will briefly describe each one of these principles. The first principle is separation of concerns, which allows us to deal with different aspects of a problem so that we can concentrate on each one of them separately. For example, if you are building a transaction management system, you worry about the functionalities of the transaction system, and then you worry about the efficiency considerations. So first you put in all the functionalities and then you optimize it later. So this is called separation of concerns. And the second aspect is modularity, where you take a complex system and you divide the complex system into a number of pieces called modules. And in these modules, we try to make sure that all the elements are related strongly, so that's called high cohesion. Also, these modules should be loosely coupled, where coupling involves the interdependence of various modules. So we want the modules to be highly cohesive and loosely coupled. The third aspect is abstraction, which is a process whereby we identify the important aspects of a phenomenon and then we ignore the details. When we were discussing about object oriented systems, we did talk about the concept of abstraction. Fourth is evolvability. Software changes, as we have described before. Now there are several types of changes that can happen. The types of changes that can happen are due to hardware, due to algorithms change, due to new features that are being added. So change is part of the process. So when you design your software, you have to design it in such a way that the software is clearly evolvable. Stage number 5, principle number 5 is generality, where when you develop a piece of software, you want to make sure that this piece of software can be used in a variety of applications. For example, take the case of spreadsheets. We develop spreadsheets not only to solve particular business application, but rather to solve a variety of applications. The equation solvers, for example, are not developed to solve only certain equations, but rather a wide variety of equations. When you build a piece of software, you have to make sure that you build in quality and not wait for the testing stage to test and to do quality assurance. That's useful to do at that stage, but it's, as I have mentioned in the previous module, that it's easier to if you catch errors during the early design stage, it costs you less to repair them than during the final production stage. So we need to build in quality. There are a number of ways to build in quality into the system. One way to build in quality is to understand what are the various features, software quality factors that the user requires, such as correctness, efficiency, expandability, flexibility, integrity, interoperability, maintainability, manageability, portability, and a host of features that the user likes to see. For this, we can engineer in some attributes into the software when we are building the software. For example, we can build in autonomy, we can build in commonality, we can build in completeness, and we can build in accuracy. So associated with these engineering features, we have the quality features with if you make sure that the engineering features are done well, then the quality features that the user wants will automatically be done well. So this is the process that whether you are developing traditional software or whether you are using object oriented software, you will have to adhere to. Finally, the seventh principle, success is defined by the user. Again, this is true for both object software or any software development, that the success of any piece of software is determined by the user. If the users accept it, if the users like it, software is successful. This is also true for engineering products. The user is the final judge. Now, if you look at the software, if you look at the object oriented principles that we have mentioned, you would see that there are a number of features that are already implicitly incorporated into the object oriented concept. For example, things such as encapsulation will take care of this modularity and separation of concerns. We talked about abstraction. We can evolve the objects in a fairly flexible manner by subclassing and adding new features. And generality, building in quality, and success are same whether you are talking about object oriented systems or conventional software development systems. So there are some features which are unique to object oriented systems, and there are certain features which are common in whichever language or whichever methodologies that you are going to use. One of the things you have to keep in mind is that using an object oriented programming language does not mean you are following the object oriented methodology. You have to be very careful in that, because they may enforce the object oriented programming methodology to a certain extent. However, you need to be careful that object oriented, just because you are programming in C++ doesn't mean you are using an object oriented methodology, and people do this mistake all the time, and you have to be very careful while you are doing that. So here is one view of object oriented software development. This is based on some conversation with Phil London at Lotus 123. The way we develop our software, you will see some examples of the software later on in module 5, is the following. First, we spend, like in the traditional software development, a lot of time on the analysis part, where we do object oriented analysis. And once we do that, we go through object oriented design, and then we code and test it in an appropriate language. This is after the fact that we have done conceptualization and things like that, and this doesn't also take into account maintenance and marketing. By the way, in most software, maintenance plays a major role, and there are various numbers in terms of how much maintenance costs more than the design and production of software. So in this process here, we spend lots of time on functional requirement analysis and the design stages, and we don't spend too much time on the coding and testing in stage 1. We are only prototyping, checking to see whether the language offers the features that we want, and maybe develop a small prototype or not. So this is stage number 1, and I will talk about a system called Cosmos, where we went through the several stages, and right now it's in stage 4 or something like that. But someone asked me a question some time ago, when does software development end? And my answer to that question is, it never stops. Software always evolves. It's evolving, and it keeps on evolving unless someone shuts it out and puts it somewhere else. Otherwise, any piece of software, if you look at Microsoft Word or MS Windows or so on, all these pieces of software, they keep evolving over the period of over several years. The requirements change, the hardware changes, and the new features are incorporated, and so on. This kind of methodology facilitates that process. For example, in this thing, in stage 2, we spend more time. We increase the time we spend on code and test, and we decrease the time we spend on analysis. But keep in mind, the analysis doesn't go away. It's always there because requirements keep coming in all the time, and then we kind of spend an equal amount, a lot of time on design. We keep spending time on design. Then as we go through, we reduce the time that we spend on design, we reduce the time we spend on analysis, and we increase the time we spend on coding and testing. And doing this process, we follow the object-oriented analysis, object-oriented design, and coding and testing. So what is object-oriented analysis and what is object-oriented design? In the next segment, I will talk about object-oriented analysis and object-oriented design. Object-oriented analysis is a method of analysis that examines requirements from the perspective of classes and objects found in the vocabulary of the problem domain. So in object-oriented analysis, we look at the functional requirements from the perspective of class objects which are found in the vocabulary of the problem domain. And when we talk about an example, we'll see how this works. And object-oriented design is a process where we do the decomposition and then we develop a notation for depicting both static, dynamic, and functional models of the system under design. Again, when we talk about notation, I will discuss on how you describe static objects, how you define the functional models, how you define the dynamic models. So the overall steps in the object-oriented analysis and design are the following. You identify key objects and their relationships, identify the structure, identify the internal behavior, identify the interface behavior, develop these class hierarchies, and implement each one of these objects. Now when you are doing your analysis, you identify a number of objects, and when you identify these objects during the analysis stage, you can map that to the design stage. One of the advantages in doing object-oriented analysis is that the objects identified during that stage can be used during the design stage, and you draw things like state transition diagrams and so on during the functional requirement stage. There are lots and lots of notations developed for object-oriented analysis and design. So what we are going to do next is to describe one such notation, which is based on an excellent book by Rumbach et al. Entitled Object-Oriented Modeling and Design. So we will be using, with slight modification, Rumbach's notation. However, please note that there are other notations, and depending on what notation you are comfortable with, you should try and follow that particular notation. I would like to point out there are more than 24 notations and methodologies that have been reported in the literature. In the handout that I have provided, I gave you some references by Chris Kemmerer and a number of other people who have reported these methodologies in the Communication of the ACM and IEEE Computer. So you have a look at those references and look at these 24 methodologies, but I will be following the methodology by Rumbach et al. In this section and in the section on applications, where we will develop our object models using this notation. So please follow this carefully, because you will need this notation when we talk about applications of object-oriented systems. So the object-oriented notation is a methodology for representing these objects, relationships between objects, inter-object behavior, data flow, and state transition. Rumbach in his book describes 3 basic models for object-oriented modeling. One is a static model, and we have seen an example of the static model before, where you develop the objects and the relationships between objects, and I will describe that in a little more formal manner. Then we have the dynamic the dynamic model, which describes the behavior, and the behavior is how an object reacts to the external world. Finally, we have the functional model, where the function of a particular system is described. That means what the system does. So behavior is how, function is what, and we will describe these 3 models briefly in the following slides. Static model. there are several relationships that we talked about before. ISA, which describes generalization, instance of, which describes classification, part of, which describes aggregation or composition. Now, the word aggregation is used in a different sense in some programming languages and databases, where they use aggregation to mean collection objects or set objects. I am going to use aggregation here to mean composition or a part of. Let us go to the first one, ISA. The class objects are described here by rectangles shown here, and we provide a class name here. In this case, the class name is A. The subclasses, again, these are all rectangles, so we have used these are all subclasses, so we used the rectangle notation here. And the classes are related to another classes by ISA relationship, as we described before. The subclass relationship is depicted pictorially by this filled in triangle here. This particular triangle depicts, if I have this triangle, it shows that this object is a subclass of this object. It is very important that you describe these relationships pictorially, because a lot of times what happens is that you come back to the software maybe 2 years down the line, maybe 6 months down the line, and the pictorial definition is much more useful than English like definitions. There is another definition, that is the formal definitions, which are very, very good, but only problem with the formal definitions is lot of people, lot of programmers are not very used to formal mathematical notations when they do their programs, and there is an argument on this aspect in the literature right now. I do not want to go into that. In terms of the classification, the individual objects are represented by these rounded rectangles, and again here we have the class object represented by this rectangle, the individual objects represented by rounded rectangles, and the instance of relationship is just represented, we represent it through this arrow. Now, what one can do for this particular classes is the following. If you want to put in the attributes and the method name, you can do that too, as we will show in the application section. I can take this object and divide it into various parts. Like I can take this particular class object and divide it into 3 parts. In one part I can have the name, in the second part I can have the private, I can have the structural variables, in another part I can have the behavior variables. So, I can divide this class into 3 names. Again, it depends on your convenience of doing this one. In terms of the aggregation, I represent aggregation by the following. Suppose f is a part of A, it is represented by this diamond here, and then there is a straight line. Now, if you look at this particular part of the slide, you will see several things. You will also see certain annotations here. There is a relationship between A and F, that means F is a part of A, but then you see a number called 1 here. What it says is that this A should have at least one F as a part of. That means there must be at least one F. As an example, if you are developing a user interface, you want to have at least one main window. So, to have at least one main window, the way you represent that is by having this F as a, by having this notation 1 here, saying that you need to have one of this thing. If suppose I put 1 plus, it says at least. Suppose I plus 1, it says only 1. So, if I add an plus here, it says at least 1. If I just have 1 here, it says it should have at most 1 and no more. So, here we have a circle which is filled, and then we have this diamond. It says that there can be 0 or more of G. That means we can have G, whereas n is going here from 0 to I. I can have 0 of G, or I can have more of G. In other words, if I have the window and then there may be sub windows in there may be 0 sub windows, or there may be more than 3 or 4 sub windows in there, and we will see some examples of these windows later on in the application section. So this relationship here is a little different than this one. This one says that G can belong to only A, only one of A, whereas this one here says this is a many to many relationship here, where a many H can belong to many of A and A can have many of H. So that's the relationship between H and A. So this is a many to many relationship, and this relationship here, especially when you're talking about relational model, you must have seen the entity relationship model. So I'm trying to explain that in that way, whereas this one shows many to one relationship. This one shows one to one relationship. There are other relationships that we incorporate in there. For example, B not only can be just ISA or something like that, B can be related to C for something using some other relationship such as works for or has a and so on. So we can have other types of relationships here. One of the things you can do is you can have this association name as a class by itself with its own structure and own behavior, and that's represented by this, where you have these two classes B and C connected by this semicircle here, and then you have the association name, and then you have the structure and the behavior. Again, we'll see that as we go in the examples. We see in the application section we'll see some examples of this. The derived association here in this case, the class C is derived from class B by doing some operations. That means the class C may not exist by itself, but it might be derived from class B, and this is a kind of a funny notation here where you use a cross bar here, and again we will see an example of this in the application section. So I'll clarify any questions you have in that section. And this is, and there are more sections which is given in Rumbach's book, but I'll talk the two other models so that we can go through the example in the interest of time. The next one is the state transition diagrams, and these are very useful as for the functional requirement stage, and not only that, they're very useful for developing models of the user interface without writing the actual code or without doing the actual pictures. In states are, a state is a collection of one or more objects, and states change constantly. They're time based in a way. Like here I have one state, and then I have another state. Now the way this is represented here is that if states change, if some events happen to change, if this states to this state, for example, if I send a message to this state here in the form of an event, this state changes to state 2. However, while doing this, it might produce an action, or you might have to check some conditions. For example, if I have one of the states could be a pointer on an item, and then the event is if I take my mouse button and press the right button down, the action could be display pop-up menu, and then I go to a state called menu visible, and I can be in that state constantly until I remove my right button up. I don't have any preconditions here. This example shows this in a more clarified manner, where this is one state. Remember that these are all objects here. There is this menu object here, this file object, these are all file object, edit object, view object, text object. So in this state, I press a button on this file object. When I press a button on this file object, this menu is visible, so I get into a state here, and in this state, I have the menu shown, and then when I take this pointer here and move it down, nothing happens. I am in the same state. Unless I release the button, I go into some other state or something like that. So I can describe that using this state transition diagrams, and you can define the behavior of how your vehicle moves and so on using the state transition diagrams. The next model is the functional model. The functional model has three components essentially. There is a data store, there is a process, and then there is an agent here. Now the data store is like your object-oriented database system. This is then you get data from this. The process gets the data, and the process puts back the data. Similarly, the process is the one where it takes the data in, makes some manipulations. Like for example, this process could be a plus sign. It can take 5 and 4 and return 9 here. So that's a particular process. So this process takes the data in and process spits the data out either to an agent or to a data store. And in a traditional functional model approach, the data store is generally represented by these two straight lines. The process is represented by this oval object, and the agent is represented by this rectangle. However, in the object based functional model, I would like to describe this in the following manner. Since everything here is an object, I describe my data store, my agent, and my process in a uniform manner. Everything I have it in a very uniform manner, as is shown in this figure, where now this particular data store can send data to the object, which this object could have some name, and the process I just depicted by this oval with this red color in here, or you can use anything you want. And from here I send data to the agent and I receive data from the agent. So let's now go through an example to see how we can use the concepts which I have presented in building a small system. Take a few seconds to read this. It's given in your handout, but anyway I will read this out for you. The idea is the following. The idea is to build some buoy software. So you have a collection of free floating buoys that provide navigation and weather data to the ships or aircraft which are in the near vicinity. And these buoys, they collect air temperature, water temperature, wind speed, and location data through a variety of sensors. And each of these buoys can have different number of wind and temperature sensors, and they be modified to support other sensors in the future. That is the extensibility or the evolvability. The buoys have a radio transmitter, a radio receiver. Each of the buoys some of the buoys might also have a red switch which can be switched on and off by a passing vehicle, or they might have some kind of a red light which can be activated by a sailor in a passing ship, or maybe some aircraft which is in the vicinity. Now this is the problem description, and here is an example of that one, where we have a number of free floating buoys. We have some ships around. There is a red light and a red switch here, and red light and a switch. The switch may not be may not be in some of the buoys, or it may be in some of the buoys. So the color of the switch could be red or need not be red. I just use the word red, but it need not be a red switch. It could be any switch which could be switched on or off by the sailor. So what are the specifications for this software? So this example is taken by a paper by Booch, and Booch has also written a book on object-oriented design, which presents a different notation for object-oriented systems, and you might be interested in having a look at it. It's again in the references that I provided along with your handouts. The software specifications are as follows. We have to maintain the current wind temperature, current wind speed, current water temperature, and location information. The wind speed readings are taken every 30 seconds. The temperature readings, that is the temperature of the air and the temperature of the water, is taken every 10 seconds. Again, it's taken every 10 seconds, where the wind speed readings are taken every 30 seconds. Keep that in mind. The wind speed readings are taken every 30 seconds. The temperature readings are taken every 10 seconds. Even the location information is also taken at every 10 seconds. So there's a clock which is sampling these things. Now the wind speed and the air temperature and the water temperature are kept at a running average. So you constantly compute this particular average. So a process may be computing this average. And at every 60 seconds, you broadcast the current wind speed, the temperature of the water, and the temperature of the air, and the location information. Again, you broadcast wind speed, temperature of both the air and water, the location information from the past 24 hours, if someone requests the particular information. You can activate or deactivate a red light based on request from a passing vehicle. You can continuously broadcast an SOS signal after a sailor comes near the buoy and engages the emergency switch, which can take any color you want depending on your fanciness in there. And then you can reset. What happens is that once someone sets the emergency switch, you keep sending the SOS signal until someone else resets it. So these are the software specifications or the functional specifications. Now if you look at these functional specifications, we can identify a number of objects in here, and here is a functional diagram which let's look at the objects in the scene. This particular slide is not there in your handout, but I'm going to describe it briefly. If you look at the objects in the functional specifications, we have identified these objects. There's a clock object, which is the one which sends pulses either every 10 seconds, every 30 seconds. We have the wind speed sensors. We have the air temperature sensors. We have the water temperature sensors. We have the location sensors. So these are all class objects that we can identify in the functional specification. We have a database, which is the sensor database. There's a message switch which can be switched on or off. There is a radio receiver. There's a radio transmitter. We have the emergency switch, and then we have the red light. Based on all these objects, we can draw a functional diagram which is like this, where we have a clock sending the pulse, and the wind speed sensors, depending on what the nature of the specification is, reads the wind speed, and the temperature sensors take the air temperature information. The water temperature sensors take the water temperature information, and the location sensors take the location information. And remember, in the functional diagram we have this oval shaped units which are the processes, and we are soon gonna take this out in the object diagram. We can just move this from here into the object. So in the object notation, we encompass all these things in one object as such. So now these things take the average values, whereas in the location we just calculate the location, throw everything into the sensor database. In the traditional model, this is shown by these two lines, and the sensor database spits out the data of wind speed, the temperature information, that is air temperature, and water temperature, the location information. It broadcasts to some other unit, would broadcast the message, and that is also done based on this pulse which comes from this clock here. So you send messages to the radio transmitter, you send the SOS message to the radio transmitter, and the emergency switch is the one which does the SOS request, and the radio receiver sends a request to this unit here which can broadcast the messages, and the radio receiver also can set the light state to a red light, as we have seen in the previous slide. So if you look at the object notation for this, we have now the various objects, that is the clock object, the wind speed sensors, the air temperature sensors, and so on. So now this is how we draw the objects with this information flow across various objects. Now let's have a look at this at some of these objects. We can draw a taxonomy of these objects. Like here is an object taxonomy, where we have at the top level the object. There's a clock object, which is a subclass of this object. There's a sensor object, which is a subclass of this object. There's a database object, subclass of this. Then we have the speed I have not used the word sensor here, but this is a speed sensor object, which is a kind of a sensor object. Then I have the wind speed sensor object, which is a subclass of the speed sensor object. The location object, which is a subclass of the sensor objects. For each of these objects, then we got to determine what goes in, what goes out. So we have to determine the structure and the behavior for each of these objects. For example, if I take the sensor object, I want to know what that sensor object does. So, if we can look into these objects like this and say what does the sensor object do, or what does the wind speed sensor object do. Remember that we have taken all these objects and the location sensors, water temperature sensors, air temperature sensors, and wind speed temperature sensors, and abstracted into a sensor object. Now, there is a question here. The question is, when do you abstract them out? Because in this thing, if you look at this object diagram, we do not have the higher level, we do not have the sensor object around here. Now, there are several ways of working this. Now, one way to work this one is the following. You can say, well, I have a reusable object called the sensor object somewhere in my database. Now, this sensor object actually has got a lot of things which the wind speed sensor, the air temperature sensor, or the water temperature sensors do. So, I can maybe subclass it that way. That is one way of doing it. The other way of doing it is, if there is no reusable object, I will look at each one of these objects and say, what are my inputs, what are my outputs, what are my inputs to the wind speed sensors. So, I have to say, well, the wind speed sensor gets a message from the clock every 10 seconds. And then based on this, it's either 10 seconds or 30 seconds. It's about 30 seconds. The winds, as you have seen here, the wind speed readings are taken every 30 seconds. So, every 30 seconds, this wind speed sensor gets a message from the object. So, that means this is the interface to say a message from the clock object, sorry, it gets a message from the clock object. So, whenever the wind speed sensor gets a message from the clock object, it has to do something. So, it does some operation in there. What is the operation it does? It goes and measures the wind speed. So, that is the internal operation that it does. So, what else it does after that? After it does that, it has to put the value somewhere else. So, it puts the value into the sensor database. So, what are the three interface functions that we need to provide to the wind speed sensor? The three interface functions that we need to provide for the wind speed sensor are the following. One is get pulse. So, that means I send a message called pulse. Every 30 seconds I send a message called pulse. And when I send a message called pulse, associated with that message, I can have a procedure called take sample, which will be invoked, and that will take the sample. So, once it takes the sample value, it can put it into its attribute called value. That could be an internal behavior, and then I can have an external behavior. That is the third one which I am talking about. So, the external behavior is put value. So, it has to send it to some sensor database. So, it puts the value into a sensor database. Similarly, the same thing, the air temperature sensor is doing the same thing, the water temperature sensor is doing the same thing, and the location sensor is doing the same thing. So, all the sensors are doing the same thing. So, I look at this common behaviors and common structure, and then I generate an object which I call the sensor class. Now, the sensor class, if you look into the taxonomy here, is a subclass of this object. The sensor object is a subclass of this object, and the speed sensor is a subclass of sensor, the location sensor or the temperature sensor. All of them have very similar features around here. So, that is why I developed these sensor objects. Now, the advantage of this is, remember, one of the things that you have seen before is one of the specifications is that new sensors may be put into the picture. So, how do you put those new sensors? We can do it in the following manner. We can subclass it from the sensor object. So, when you subclass it from the sensor object, we can have some other sensor which maybe measures the eddy current velocity or something like that, and whatever new things that come up. So, we have an abstraction of all the sensor objects into a sensor class. So, we generalized all the sensor objects into a sensor class, where we have, in this case, we can add additional attributes we have only one attribute here, which is the value. Then you can have in terms of the behavior, we have put value and then we have pulse. Put value invokes a procedure called put value, and pulse invokes a procedure called take sample. Now this is a very, very simple example that I have illustrated, but this is simple, but on the other hand it illustrates many of the concepts that we have been talking about object oriented analysis and design. Note however that this example did not use all the things that I have mentioned before. It did not use the dynamic model that we showed. It used some of the functional module, and it did not use all the relationships we talked about. It only used ESA in relationship in there that we showed. Of course, the specific things that we have not talked about is that there are instances of specific objects that we create, which are instances of this wind speed sensor and instances of this airspeed sensor, which are actually located on the real world objects which we saw in this example. So there are these are all individual unique physical objects that have a unique identity, and these objects are instances of the objects that we have seen here in this case. So those are all, you make instantiation of that. You cannot make further instantiations of this object, but these are individual objects which we create in this simulation package. Later, however, in the module on applications, we will go into this a little more detail and talk about some of the applications that we developed where we use a number of features on the object oriented analysis and design that I have discussed before. Now to summarize, object oriented software development has several advantages. The object oriented programming concepts have several advantages. Modular, because objects are modular units, we can develop code in a modular manner. Evolvable, as new features are wanted, we can add these features into the object model very easily. Reusable, remember the sensor object that we talked about, sensor class object, and that class object can be reused in a number of situations. So these objects are reusable. So as a result, you reduce the time to develop software. Then you end up in a smaller code size because of inheritance and so on. We can develop into a code size. The other thing is predictable. That is, using this object oriented software, we claim, this is again a claim, it has not been really proven as such, that the software development process is predictable. However, one of the major problems with the software development process is that the software timetable that we are talking about, we always overshoot. Now this is a problem whether we talk about either object oriented software development or regular software development. We tend to overshoot our time schedules. However, object oriented software development reduces the time because of all these features, and hence it may allow us to produce software in a lesser time. So what are the architectures that you are going to see in the futures? The typical architectures that you are going to see in the future are the following. This is you can see this trend with IBM and Apple teaming up with the digital equipments, the new machines coming up, with HP's new architectures coming up, and so on. There are a number of companies out there who are going through this to these architectures. At the lowest level, we might have a distributed object oriented operating system. In fact, there is a group called Object Management Group was trying to decide a standard for the object model as such. The operating system is distributed. Over this, instead of having the traditional file system like the Unix file system, we are going to have an object oriented database management system in the future. In terms of the languages, we might see several over the databases. We might see object oriented programming languages such as C++, Smalltalk, and Ada built over object oriented database systems. So these are extensions of the current C++ languages but provide persistence automatically here. And there's a language called E, which is developed at University of Wisconsin-Madison, which provides an extension to C++, so we have persistent classes. Similarly, the commercial database people such as Object Store, Objectivity, and other people, Ontos, they provide you an extensions to the commercial to C++ so that you can develop, so that all these objects could be persistent. And over it, we will see the emergence of software libraries are the class libraries. For example, the National Institute of Health class library is one of them. And there's an inference engine library that we have developed in our lab, and I will talk about it later, how we use that in our code in our various applications. So we'll see these class libraries, and they will be distributed in the public domain, or you can go and buy it from various sources. Over this, we will see user interface modules and case tools. I will talk a little bit about case tools in object-oriented the object-oriented case tools which are in the market later on during the applications, during the comparison of various tools section. And over this, we will see application programs being developed. So this is the kind of layered approach that companies should take in the future. Again, this is an opinion, and we can support multimedia objects, voice, audio, and all kinds of things within this framework. And this is a framework which is very flexible and poses a number of advantages. In terms of software development as such, the software development will take a collaborative framework where we have, just like the design framework that I talked about, we'll also have the clients, the designers, analysts, programmers, and the managers, all of them talking through an object-oriented database or a repository. And there is a trend towards this in some of the universities. For example, Columbia University has a product called Marvel, which facilitates this object-oriented software development in a collaborative manner, and it has certain nice features such as collaborative transaction model for multiple people working out of the same database. However, we still need to study a number of elements here, such as the metrics. We have some work being done at MIT by Chidambar and Kemmerer in terms of developing a set of metrics for object-oriented programming and object-oriented software development. The other thing, two concepts that we need to look at is the organizational issues. That is, how can you diffuse the object-oriented methodology and concepts into the current setups where people try to use people are so used to COBOL and other kinds of traditional programming techniques. So this is an organizational issue and needs to be looked at, and the management should be committed to this process. One way to do this is maybe to do it informally between various groups, and maybe once the management sees the advantages of this process, they can go ahead and make it a formal way of doing things. Finally, object-oriented tools should be effectively integrated into other packages. The case tools that are being sold in the market should be integrated into other tools, into your application programs, and things like that. And that ends module 3. And in module 4, we will compare a number of commercial object-oriented systems, both the programming languages and the databases. And finally, in module 5, we'll come to applications, and we will demonstrate how we built a number of applications using the techniques that I have mentioned so far. Thank you.